Hello everyone. Today we are going to have a brief introductory topic on finite element analysis. So I'll be giving you a brief idea on what is finite element analysis, what are the different uh, important aspects of finite element analysis that we generally use in Ansys and other commercial softwares. It will be covering a background of how inside a FEA software works. So moving to the main topic. So I'll be covering these contents today, which are the methods of the solution, finite element method, and what is discretization of domain. Then we'll talk about few components of finite element, which are nodes, elements, and state functions. Then we'll be talking on we'll be taking an example, which is a linear static analysis, and we'll explain different mathematical aspects that are there in the finite element methods. Then the application of finite element, its advantages, and we'll be covering few examples on finite element analysis. So before going to finite element analysis, let me say what an engineering analysis is. Engineering analysis is like finding a solution to a physical problem, say like I am having a cantilever beam or some machine part. So whether the part is going to work as it is designed. So when we try to solve and analyze those situations, that are called engineering analysis problems. And there are again two parts. One is a classical method. Classical method is like our general approach that we follow. Like we solve a different a set of analytical equations for based on the problem, and we'll be getting a solution. So that is the classical method. And we have numerical methods. Numerical methods are a kind of approximation methods where we solve some set of partial differential equations or some kind of equations which are maybe linear equations and all those, and which will be representing a physical problem. So let's go into it in details, or like methods of solution. Again, as I was saying, it's a classical method is there. They offer a high degree of insight to a problem, but the problems are difficult or impossible to solve for anything but simple geometry and loading. Like if we have a complex geometry, it will be very difficult to solve using a classical method. We have the advantage of numerical analysis method when the components are complex. Say a big pipe is carrying some fluid through a very complex uh, trajectory, or like a very complex machinery is working, and we need to find the stress or the loads that the machine can withstand. So in those kind of complex problems, classical methods fails to solve because the equations that forms the physics of the problem becomes very complex and will not be able to solve it. In those conditions, we will be using numerical methods. Numerical methods are a kind of approximation methods. They will not be giving you the exact solution to the problem, but they will give you a very close solution to the problem depending upon the discretization, or depending upon how we are using those methods. We have energy method, and like it is minimize an expression for the potential energy of the structure over the whole domain. So it's representing a system in the form of potential energy, and equation be like we will be representing the system in a form of equations, and we'll be solving it. Then we have boundary element method. The boundary element method is a numerical computational method of solving linear partial differential equations which have been formulated as integral equations. So we are formulating the system as a set of linear partial differential equations, and we are solving it to identify displacement or many other parameters. Then we have finite difference methods. This finite difference method, or then finite volume method is these two are mainly used in flow analysis, like fluid flow is there, and we try to identify the fluid properties like mass, flow rate, velocity of the flow, like that. There we use this finite difference method. And the theory is like a finite difference method is a mathematical expression of the form f of x plus b minus f of x plus a. The approximations of derivatives by finite differences play a central role in the finite difference method for the numerical solution of differential equations, especially boundary value problems. These boundary value problems is specifically because these boundary value problems are mostly flow problems, or where the flow is going to happen. So there we use finite difference methods. Now we have finite element method. So a finite element method is a numerical technique to obtain an approximate solution to a class of problems governed by elliptical partial differential equations. Such problems are called boundary value problems, as they contain partial differential equations and the boundary equations. So it's this finite element method is also so a boundary value problem plus there will be partial differential equations that gives an idea on the geometry or it captures the stiffness of the geometry to partial differential equations. There are a lot of mathematics are involved in finite element method. All these numerical methods involves a good amount of very complex mathematical equations, and they when we look into it, they will be linear equations, but the amount of equations that will be there inside to solve a very complex problem will be very high. So we will be discussing on finite element method in this course in detail. Why we are discussing on finite element method? Because mostly the structural problems where I'll be conducting more tutorial on Ansys will be using finite element method to solve the problems. So as we said, FEM is a numerical method for solving a system of governing equations over the domain of a continuous physical system, which is discretized into a simple geometric shapes called finite element. So what this says is, this is a method for solving a system of governing equations, and these governing equations are formulated over a domain of continuous physical system. So we will have a continuous system. The continuous system can be anything. It can be a small beam which is held at one point and free at the other end. Two, it can be a very complex machinery which involves large number of components, large number of joints, large number of bolted components, all those things. So that forms our physical system, and this physical system is discretized into small shapes, simple geometric shapes, which are called as finite element. So in effect, what we do is we will have a continuous system. It can be time dependent or time independent systems. This system will be divided into small systems, or which we call as finite element, and they will be represented as linear algebraic equations. Say we call ordinary differential equations or partial differential equations. So this is a very brief theory idea or a brief wording for finite element method. Let's see what are the different in the detail. What are the different components of a finite element method? Or this is the rather than components, I would say these are the different steps that are involved in a finite element method. So first step is discretization of the domain. Say as I was saying, our continuous domain or the physical domain need to be discretized into finite elements. So the modeling of a body by dividing it into equivalent system of finite elements interconnected by a finite number of points on each element called nodes. This is the definition for discretization. So when I explain what is discretization, this is the concept. Like you have a continuous domain. In this example, it's a beam or a rectangular geometry which is fixed at one end and there is a force at the other end. This is a continuous domain, or this is an infinite degree of freedom domain. Why I say? Because this physical domain I can divide into small pieces of infinite number of small pieces, and each of these small pieces can have 6 degrees of freedom. Since the number of domains are infinite, or I mean since the number of divisions I can make on this continuous domain is infinite, we will have infinite number of degrees of freedom for this domain. So based on our need, we will be dividing this domain into finite number of elements. So this is the after discretization, this is the condition of the domain, our physical domain. We will have 1, 2, 3, 4, 5 elements will be there, and each element or subdomain, what we call, will be connected through nodes. Nodes are like interconnections that form or that connect the elements or subdomains in a finite element discretized body. So you can see this continuous domain is discretized into a 5 domains. 1, 2, 3, 4, 5. 5 subdomains. So there will be finite number of degree of freedom for this body, while the continuous system has infinite number of freedom, which we may not be able to solve using other than our analytical methods. This will be very difficult to solve. When we have a finite number of domains, we can we can solve those finite number of domains for the various physical quantities of our need. Moving forward, now this shape functions are very important for finite element analysis, because these shape functions are the functions which interpolate the solution between the discrete value obtained at the mesh nodes. Basically, if I say these shape function are the equations that are used to represent one node. So like this, based on the number of nodes, you will have n number of shape functions formulated. So say I have for this node P, we are using a linear equation. Then all the nodes connected in the P in that element will be having a linear equation. And again, if I want to have it a quadratic function, then I can use a quadratic equation. It will be in the form ai plus bx plus cy plus dz plus bx square plus cy square plus dz square. Similarly, some kind of quadratic equations will be used to represent those shape functions. So this is a tetrahedron, and I am assuming a linear shape function for it, which will be in the form of ni equal to in the space domain we can represent as ai plus bx plus cy plus dz. Like all are linear functions. So hence we call this a linear function. If I am having it as a quadratic function, like x square is a bx square plus ci y square plus di z square plus some more will be the interactions and everything can come, then that will form a quadratic equation, quadratic polynomial. So it will be a quadratic chain function. Or we can use any higher order shape functions for representing the nodes. As our order of the polynomial increases, our computational cost also will be increasing. It will be difficult to solve those higher order equations. So now we will be seeing what are the steps that are involved in the process of finite element analysis. So now we have seen, like, we are discretizing the domain and we are having equations at each node. So how these nodes satisfy the physical properties of the system that we are discretizing? So for this, we need to satisfy these conditions. We need to satisfy equilibrium equations, we need to satisfy compatibility equation, then we need to satisfy constitutive laws, and we need to satisfy the boundary conditions. Boundary conditions involve, like, if some loads are acting on the geometry or the geometry is getting fixed at some places, the corresponding boundary condition need to be included as a part of those equations. Then only our system will be actually behaving like what the actual physics is applied on that body. So in order to get all these things, we need to satisfy these conditions. And once we formulated the equations, we need to solve those equations, right? Without solving, we will not be getting our desired displacement or stress or anything. So there are again two methods are there. One is force method and one is displacement method. In force method, my internal forces will be unknown. So I will not be knowing what are the forces that are getting applied on the system. I will be assuming like the system is having, it is moving by this much distance, and so what are the forces required to cause that movement. But it is a kind of very unrealistic condition, because generally what we used to see is in our engineering problems, we know our system, say it can be a complex machinery or a rotating shaft or something. We know at what are the forces that are acting on the shaft generally. Like I know the shaft is rotating at this many rpm, or the compound is lifting at this much weight of bodies, or weight, or this much load, or this much force is coming on that body. That we used to define a system with known quantity of forces. Then our displacements becomes unknown. We don't know how the system is responding to that. To solve that, we will be using displacement method. There are the nodal displacements are the unknown, and we solve for them. Again, for computational purpose, the displacement method is more reliable because its formulation is simple, and most of the FE softwares in corporate use this method. It is simple and it is more realistic to our physical or our physical system that is there, or it is more near to the engineering solution that we are looking for. So most of the finite element uses the displacement method in their analysis. So let's now take a example problem, or now I'll be explaining in a step-by-step manner how a software like Ansys or something will be doing a finite element analysis. This is a very crude for a theory that we'll be explaining in this course. In actual case, this will be a very complex uh, form of metric systems will be formed. Its formulas are very complex and lengthy. So we will not be going through those details. We will be just trying to understand how a physical system is going to be represented in a finite element method, in a finite element analysis, and how we are solving it. So we will be having our geometry. It can so in this example I am showing a simple cantilever beam which is attached at one end and a P force is applied on the other end. So we'll be getting the geometry from the CAD software, or we will be building the geometry in uh, our any CAD tool will build the geometry. Now we can represent the geometry in three different ways. It can be a one-dimensional problem, it can be a two-dimensional problem, or it can be a three-dimensional problem. In one-dimensional problem, this cantilever beam will be represented as a single line, and when it comes to a two-dimensional problem, it will be a surface. And when we have a three-dimensional problem, it will be our regular cantilever beam, which is solid in nature. And if I can consider, there can be a one more case where it can be a time dependent. This load is going to vary over the time. So then it will be like a time dependent problem, a 3D model which is time dependent. So that it's a different case since we will not be dealing into a time dependent problems in the beginning. So I am not going to the details of time dependent solutions. So moving next. Now we need to construct the finite element model. Like I had said earlier, we need to discretize the domain or our cantilever beam into small elements, or which we call as the mesh. Here also we have a 1D element is a line, a 2D element is a small square box or a triangle. These are the available, or the more which are the general elements that are available in all the commercial softwares. We will have a square, we will have a triangle, and when it comes to a 3D element, we will have a brick element. That is what we call a 8 like this is in the shape of a brick, and we can have a tetrahedron also, which is a 3D form of the triangular element. Now next thing is like we will see how many number of elements are there. Like I said earlier, we will be going to discretize the domain into a finite number of elements or subdomains. In the previous example also we have seen like we have discretized that cantilever beam into 5 sections. So that total number of elements that we are discretizing the component is called as mesh. So in 1D again we can have a connection of all these elements will be there. In 2D we are discretizing this into a kind of into many number of elements in 2D plane, and in 3D we will be discretizing that rectangular block into small uh, square elements or triangular elements. In this example I am showing square elements. So this forms the discretization part of the final element analysis. So here this is a very complex geometry which is discretized using these two basic elements. You can see this it's a very complex rotor of a steam engine, steam power generation unit. You can see this, all these elements are small elements are there, and this entire component is represented by this small number of elements. So this is actually a mesh from an engineering problem. I have just included to show the extent of the mesh that can be formed in a finite element analysis. So moving forward, let's see the shape functions. We will be select for a 1D element, we will be selecting a line. It can be a linear equation which has only x domain is there, which is which is a 1D element. Now when it comes to a 2D element, we'll have ax plus by plus c or something, another constant. In 3D, we'll have x, y, z equations. These are linear equations. We can have quadratic equations or other polynomial equations can be used. Now we will be defining the compatibility and constitutive laws, like epsilon equal to du by dx. That like these are all forming a partial differential equations, and this partial differential equation should be satisfying the constitutive law and the equilibrium equations. Now, how we will form this elements, or how we will join all these elements in a mesh together. So we will be using a stiffness matrix and we will be formulating the elemental stiffness matrix and equations. There are again three methods are there, like direct equilibrium method, work or energy method, methods of weighted residuals. This methods of weighted residual is one of the majorly used methods for forming the stiffness matrix and the differential equations which can be used. Now once we form this differential equations for one element, we will be forming it for the system. In a system, there will be large number of elements will be there. Then there will be forces acting on the system, and we can represent them in this form. Like my stiffness into the displacement will give the force that is acting on the body. Here, as I said earlier, this displacement term will be my unknown. This force will be known to me, and stiffness of the matrix will be formulated using the these equations, and and again it will be satisfying all these conditions. So stiffness matrix is known, force is known. My unknown term is d. We will be solving for the d value. So how we are solving? So this is generally it is a simple metric solving equations are there. So it will be can be represented as d. It can be a inverse of k inverse into f. So it's like our metric solution. So again there is a elimination method is there, which is Gauss elimination method. Nastan uses it, and there's a Gauss-Seidel method is there. Now once we solve this system of equations, we will be getting our d value. Like I said earlier, here d is my unknown, which is the displacement at each nodes. So once I solve this, I'll be getting this field equations. From this field equations, everybody knows differential of displacement with respect to our x or y, or with respect to our partial differential equations. When we solve in the displacement field, we will be getting a strain field. And when we take a partial differential of this strain field, we will be getting a stress field. So we get displacement, strain, and stresses. So these are what generally we take as a output of a finite element structural analysis. Now if we are considering some thermal example, we will be getting temperature will be my first unknown in that. We will be getting the temperature. Then the temperature we will be getting the heat flux or the heat energy that is going into the system, like that. I mean it's a kind of different set of analysis there. Now these all will be there in the form of numbers in the solution, and in finite element analysis we will be trying to understand what is happening to the system under those loading conditions. So that is the interpreting the results. This is again an important part in FEA softwares. So like we will be having deformation plot. Like I have a undeformed body. Now my body will be deformed in this manner, or there will be a stress contour. My body is having a kind of stress at different regions also already, and we can see stress contours in a visual format. So generally, to conclude this in a very nutshell, my finite element analysis includes three steps. One is the pre-processing step, next is the solution, and third one is the post-processing. So pre-processing involves all the geometry cleanup, all those things, like whatever is there in the geometry, then mesh creation. So all those will come in pre-processing. Then I have the solution. Solution is the solving of this finite element, this finite element matrix, or the matrix that we get from our finite element mathematical model. And then comes the post-processing. Post-processing is where we are trying to understand what the results are coming out of the analysis. So this is an example of finite element method, or a small example of a linear analysis problem solved using, or how we are going to solve a finite element analysis using any software. This is the standard procedure, and this is a kind of very rough outline on how we are going to solve a physical problem using finite element analysis. Now, where can we use the finite element analysis? So finite element analysis can be used in can be broadly divided into a structural problem or a non-structural problem. So what all will come in structural problem? Structural problem, we can find truss and frame analysis or a stress concentrated problem, or it can be generalized to a stress analysis. Stress analysis is like, say, I have a physical geometry like a beam or a truss, roof trusses, right? So those kind of systems are there, or a kind of complex machinery is there. So I want to understand whether the compound is going to withstand the loads that are going to come onto the low body. So what we will do is we will identify the stress on the body. We will be trying to compare with the material properties, and we will see whether component can withstand or not. Then we can go for buckling problems. Buckling again is a kind of like, I will have a long beam will be there and the load will be coming from top. Even before the ultimate load is reached, my beam is going to buckle out and can fail. So that in a complex, say a kind of rig or something is there where we have many pillars are there. So each of this long pillar can form something kind of a buckling, can form kind of a slender beam or something like that, and they can buckle. So it forms a kind of buckling problem. Then this vibration analysis is a very important area where most of the failures can occur, because every geometry that is going to transfer the load will be, most of them it will be under vibration loads also will be appearing on it, because no body is going to be stationary. Some kind of external force is going to cause a vibration onto it. So we need to know what are the natural frequencies that are there in the system of that system, and whether my load is going to excite that system, and even if the load is going to excite the system, whether the system can withstand those loads. Those things are involved in the vibration analysis. We usually call them as dynamic analysis also, but there are many more important there are many more vast areas that are included in dynamic analysis. So those also can be done using finite element analysis in such a structural problem. Then we have impact analysis, where we do crash test of a vehicle, or a impact of a rocket onto a set of systems, or explosion. These all will come as impact problem. Now moving to non-structural problems. Non-structural problems are mainly heat transfer, fluid transfer, or fluid mechanics kind of problems. Heat transfer is like, say, I have having a system where there are so many heats are getting generated, or lot of waves are getting, or lot of thermal loads are there, something like a very complex heat transfer problem. Or there is a kind of flow is happening which contains a hot fluid, then I have a cold fluid flowing over on top of it. So what is going to be the net temperature on the system? Those will come in heat transfer problem. Then we have fluid mechanics problems are there, where I will be trying to understand what is the mass flow rate in the system. So those kind of systems we can solve using finite element analysis method. Then we have electric and magnetic potential problems, like, say, I'm having a motor is there, and when the motor works, there will be a magnetic field that is passing around the armature coils, and it will be producing electricity. So I want to know whether those electricity is going to generate heat. So this is a kind of combination of both electric, magnetic, and heat transfer related problems. So we can solve many complex problems using finite analysis. So here I am going to show you some few examples where finite element analysis can solve very highly complex systems, and we will be able to predict the uh, response of the body, or the what is the output on the body when we are loading that system. So you can see a electronic circuit body is there, and there will be a lot of heat generated during operation of this geometry, these circuits. So we can see where are the heats that are getting generated on that circuit board. This is very crucial, because when we operate it, if the temperature that are getting generated exceeds the material limit, or some operating limits of the some circuits, they can non-function, and whatever we will develop in the circuit will not work. So if we can know it beforehand, it will be very useful to avoid those failures. So these are a few examples of a thermal domain problem. Now you can see example of finite element analysis in a structural domain. Consider this to be a kind of some axle in a car or something like that. So what will happen if this breaks during the working? it can result in breakdown of the car, and uh, we will not be looking for any such conditions to happen in our real life. So what we will do is we will be modeling that system in a using finite element analysis methods, and we evaluating the stress or strain or what is the fatigue life of the component using FEM, and we will be redesigning if it is not able to meet our required load conditions. Then we can see vibration domain. So this is a kind of a bridge or something. So we can see how the bridge is going to vibrate during some wind load, or when the because of the movement of the vehicle, or some other external force comes, some say earthquake comes or something. Then we will be able to see how the system is going to respond to those things. That is the vibration domain. So we will be using finite element extensively in vibration domain to understand the response of the system, the stress that are getting generated in the system, or whether the system is going to get excited because the natural frequency is coinciding with the excitation source. Something like that we will be using to anticipate the failure of the system due to vibration domain. And this is the usage of finite element in fluid domain. You can see this is the aerofoil, and you can see the flow on the aerofoil tip and tips and on the inner side. So if my aerofoil design is very bad, then there will be huge losses that can happen in the system, but we will be knowing it only during the testing. With finite element we will be able to know it at the design stage itself. This is a kind of impeller. You can see the flow lines that are passing through. So visually you can see during the design phase itself. Or this is a kind of car model. You can see how the flow is happening over the car. This is a kind of racing car model only, and this is very much close related to our practical problems. So I hope you would have got a good understanding on what is the application of, or what are the areas where we can use finite element model to solve our physical problems. There are our daily life problems or engineering problems, mostly engineering problems I would say, not daily life problems, it's engineering problems. So those are the key areas of finite element analysis, and how we are using this finite element analysis in our day-to-day engineering model. We have got a large number of softwares are available, and we'll be using. There are many commercial softwares, there are many free softwares are also there. So we can Ansys is one of prominent commercial software that is available for solving finite element analysis. So again, Ansys is a kind of multi-physics problem where you can connect all these different physics together to identify the physical nature of the system. So say, because see, physical nature can be like, consider this impeller itself. Liquid will be flowing through this impeller, and because of the liquid flow, the impeller can see high stresses because the fluid is going to impact force on it. So if you do a flow only analysis, we will be knowing what is the mass flow, right? But we will not be knowing the stresses that can be generated on this impeller. So Ansys is a multi-physics. It's a multi-physics problem in the sense like I can simulate this flow at the same time I can identify what are the stresses that can generate on the system. So if there is some electrical circuit that is going inside, and if it is driven by some magnetic some current is getting generated, so we can identify then what is the heat generated through the current also. Those kind of all the many multiple physical systems can be incorporated, or the physics or the multiple physics can be incorporated into the system using Ansys. So that is one main advantage of Ansys. So so this is the brief introduction on finite element analysis, and we will be continuing our course in the next lectures, where we will be describing how we can use Ansys software in detail. Thank you.